The dance of construction and measurement. How dual vectors act as mathematical sieves. Imagine you are building a physical structure in space using two different types of tools: building blocks and measuring sticks. The building blocks, the tangent basis. In our first demonstration, we see that any vector is physically constructed using a set of blue foundation arrows known as the tangent basis. These arrows are the actual materials used to assemble the vector. You scale them up or down and place them tip to tail to reach your destination in space. While these blocks are perfect for construction, they are surprisingly poor at telling you exactly how much of each block was used if they aren't perfectly perpendicular to one another. The measuring sticks, the dual basis. To solve this, we introduce a second set of red arrows called the dual basis. These aren't used to build the vector, but rather to probe or measure it. The secret to their success is a property of blindness or orthogonality. Each red measuring stick is designed to be perfectly perpendicular to every blue building block except for its own partner. Because of this design, when you use a red stick to measure the vector, it acts like a mathematical sieve. It kills or ignores any part of the vector that was built using the wrong blue blocks, allowing it to perfectly isolate and extract the exact amount of its partner block used in the construction. The compensation effect. Nearly parallel systems. The true power of this relationship is revealed in our second and third demonstrations, where we make the blue building blocks nearly parallel. As the blue foundation arrows begin to squash together, the red measuring sticks must perform a dramatic mathematical dance to stay accurate. To maintain their ability to ignore the wrong blocks, the red sticks must rotate outward and stretch significantly in length. This highlights a critical intuition about stability. When your building blocks are nearly pointing in the same direction, your measuring tools must become extremely long and sensitive to maintain the integrity of the system. The consistent result. Despite all the stretching and rotating of the coordinate system, the actual measured values, the components, remain rock steady. As seen in the animation, even as the floor of the coordinate system shifts and the red arrows grow to massive proportions, the numerical information extracted by those probes stays exactly the same. This demonstrates that the relationship between a vector and its underlying basis is preserved by the dynamic adjustment of the dual basis.